Hello, this is Team 16 Route0x. We are introducing you our project, Road Condition Analysis using Deep Learning. The problem we are facing. In real field work, especially humanitarian and development missions, teams often drive into places where the road condition is unknown or outdated. That slows missions, complicates planning, and increases risk. Instead of relying on memory or scattered notes, we want a simple, repeatable way to know what the road actually is, asphalt, paved or unpaved, right when it's needed. That's why we're building a pipeline that lets field teams capture what they see, turn it into clear labels, and share those labels so the next crew can plan better. This is useful for organizations like the United Nations that work across remote or rapidly changing areas and need consistent, reusable road condition information. But we have found the solution. After a long time of brainstorming and discussions, our team settled on a practical solution. Instead of memorizing the correct path by experience, we use deep learning at the core. Our system looks at video or photo captures from a phone and classifies the road surface as asphalt, paved, or unpaved. The results are then saved with time and place so the data can be shared within the team and shown on a map. That way, when someone heads to a remote area next time, they already know the likely road surface and can choose a safer, faster route. Implementation of our idea. We built an Android app that handles the full flow, data collection, processing, classification, and visualization. First, data collection. Use the phone's camera to record short videos or take single snapshots. At the same time we read the phone's location and orientation, so every image has a time, a place, and a pose. Second, processing. After recording, we extract frames at a fixed rate, for example, 1 frame per second. Each frame gets a clear timestamp and is matched to the nearest sensor reading from the same moment. Third, classification. A lightweight model predicts the label such as asphalt, paved or unpaved for each frame or snapshot. Lastly, visualization. We upload the image plus its metadata to the cloud and render it on a map with color coding, so people can read the result at a glance. Technologies we have used. We chose tools that are reliable on phones and easy to reuse later. Android Studio plus Camera X, our development environment and camera API for recording smooth video and taking stills. On-device sensor capture, we log GNSS, latitude, longitude, altitude, and device orientation from the phone's sensors while the camera runs, so images can be tied to exactly where and how the camera was pointed. FFmpeg. After recording, we extract frames from the video at a deterministic rate, for example, 1 frame per second. This gives us consistent samples for classification or future training. OpenCV, utility use, image tasks like resizing or undistortion when we need them, before upload. Structured per image JSON. For each image, we write a small JSON file that includes timestamp, location, and orientation. In Part 6 you'll see the formal names of these formats and why they matter. Firebase, storage plus Firestore, simple cloud storage for images and their matching JSON files, plus a small index for fast map queries. ResNet 18, a compact, well-known CNN that performs well for our 3 classes and runs fast. Standards and how the Urban Digital Twin Interoperability Pilot Report helped. To make the data truly shareable and reusable outside our app, we aligned the pipeline with open geospatial standards and followed the engineering guidance from the Urban Digital Twin Interoperability Pilot. For per image pose, we write GeoPose 1.0. A standard way to express where the camera was and which way it was looking at that moment. For AI-ready datasets, we package images, labels, and metadata using TDMLAI, a simple JSON structure designed for training, testing, and evaluation across different models. The Urban Digital Twin Interoperability Pilot Report laid out a clear camera-to-AI pipeline that we mirrored. 1. Sample frames from video in a consistent way. 2. Synchronize each frame with location and orientation. 3. Write standard per image pose, GeoPose. 4. Organize data for AI with TDMLAI. 5. Publish/visualize results so others can use them. Where the UN fits, rather than saying the UN must own a separate dataset, it's more accurate to say the UN is a user group and a potential large-scale stakeholder in this ecosystem. By producing geopost-tagged images and TDMLAI datasets, our pipeline makes road condition data shareable and reusable across tools and agencies. The exact behavior these standards and the UDTIP guidance are designed to enable. In conclusion, we trust that our comprehensive road condition analysis provides critical insights for enhancing infrastructure, improving safety, and optimizing maintenance strategies. Our goal is to support data-driven decision-making for a more sustainable and efficient transportation network. Presented by Team 16 Route X. Thank you.